Hello everyone, and welcome back to NL 582, Modeling and Control of Electric Machines and Drives. And that is our first tutorial session. So I hope you had time to review your previous lectures because it's so important. We'll be just today trying to solve an extended example just to make things a little bit easier. So all the time we've been talking about, it was basically theoretical stuff, and we're trying to understand the physics behind the machine or how it's working and the basic principles that all the machine applying on when it's just doing its job. Today you are trying to put this into some sort of a realistic example and try to quantify the values we've been talking about all the time, just to make it more understandable for all of us. So this example, I think it's been taken from your recommended textbook. I think you'll find there if you try to look for it, but we'll be solving it together step by step, and I hope you just focus with me because that will be very important to conclude all the information we had so far. So in this question or this problem, it's saying that the following figure shows a simple rotating loop between curved pole faces connected to a battery and a resistor through a switch. Okay, so it is the simple machine we've been dealing with all the time. So that is your north pole, that is your south pole, and it's just curved poles like that. I hope you're seeing them. So that is a pole and that is another pole. And there is the simple loop we've been talking about, and so that is a loop. I'm just trying to make it more visible for you. Okay, and this loop rotates around this axis, so this is the axis of rotation, and it rotates around this by speed omega m, like you see here. And here are your pieces of commutators. So this is a piece, and that's another piece. And now you'll find your brushes here and a brush there should be, and now you're going out to an external circuit. So I have here a supply VB, it's a battery, a DC battery, because it's a DC machine of course, and have an external resistor like this. It represents the resistor for the loop, and it presents the resistance for the other wires, like this wire here and all the wires in the external circuit, and also represents the internal resistance of the supply itself of the battery. So this R is just a resistor that is just combines all the other resistors you wanna model. The loop resistor itself, the coil we've been talking about, and the external wires connecting this loop to the battery and the external system, and also the internal battery of the supply of this battery VB, because it's not ideal. So this resistor are just like this, okay? So I hope you understand just what's going on here. Okay, and then it's done that the resistor shown models the total resistance of the battery, the wire, and the machine. That's what I'm talking about. The physical dimensions and characteristics of the machine are, and he's just giving you these dimensions, are 0.5 meters, and R is basically this value. He's just giving it to you. There is R, and it's the radius of the rotor. So like we said before, we have the rotor like this, and that is our poles north south, and that is the rotor. And here is your loop, it's just going out, going in and going back out. So that is called side 1 and 2, if you remember all the time we've been doing. And here the radius R of the rotor. Okay, and the capital R 0.3 ohms, that's the resistor. So don't confuse it. Small r is the radius, capital R is the resistance value. VB is the supply, 120 volts. It's constant. It's just giving you there. That's supply DC voltage, 120 volts. L is 1 meter, and L is the length of the machine, or the depth of the machine, whatever you want to call it. Remember the last lecture. So this is L here, the depth of the machine, which will be also the length of your coil side. So that is L, which is 1 meter, okay? And B, capital B, is 0.25 Teslas, which is the flux density of the machine. Okay, guys? So it's very important, guys, when you all the time trying to solve a question, to think as an engineer. It's not just a mathematical problem we're trying to solve, guys. It's here all the time. Imagine in your head that you're solving a real life engineering application. That's something you want to find, okay? So all the time look at the numbers. It's very important to have this in your mind. It's not a mathematical problem. Whatever calculation, whatever numbers you have, that's fine as long as you're doing it mathematically right. No, sometimes the number will look very stupid. That's what I'm saying. It's just, if you're trying to solve a problem, your numbers has to be realistic. So students come and just say, I solved this whole problem correctly, but I just got confused while calculating some numbers and it just gave me a wrong number just out of confusion. Okay, yeah, it happens, and yeah, it's not a big problem unless this confusion leading you to have a number that's totally non-realistic, and that means you don't understand what you're doing, and that's a problem. Not just to pass a course, but in your life, in your professional life. That's what I mean. So for example, the flux density he's seen here is 0.25 Teslas. So the typical flux density to find in machines will be less than 2 or a little bit higher than 2, okay? So if you're just trying to solve a question and asking you to find him the flux density, and you find me calculating the flux density to be 2000 or something, it's not a problem that you have a number wrong. But if you leave the number like that, that means you don't understand what you're doing, and that's bad. Okay? So if you encounter something like that, you are solving a problem, that means 100% you have a mistake. You just made a mistake. So go back and just figure out what's happening. And if you go back once and once more and I didn't find this mistake, just leave a hint below this number, and this, I know this number is wrong. Okay, that's very important, guys. So keep that in mind. Also, the resistance here is 0.3 ohms. It has to be low because this resistance represents the losses in the circuit. So all the time you have this, it's represented the copper losses in a system. Okay, it has to be small, otherwise this system is very poorly designed. Okay, guys. So that's what I'm saying. Do not just go over the numbers and just leave it like that. No, look at the numbers. It's important, okay, because the numbers your whole life as engineers. All the time you will be taking decisions based on the numbers. So keep an eye on the numbers all the time. And while you're solving any problem, just look at the numbers that came out of you step by step. Do not go to the next step unless you're seeing the number you get in the previous step to be realistic, engineering wise realistic. Okay, guys? Yeah, so the first question, number A, he's saying what happens when the switch is closed. So here you have a switch here. So before closing the switch, there is no supply and there is no anything here. He's not having any voltage applied to this loop. So he's saying what happens when the switch is closed. Okay, it's theoretical stuff we need to tackle. And that's a very important thing. I need to have your mind with me for it. Okay, guys? So it is the same theory of operation I've been discussing all the time. Okay? So when the switch is closed, okay, and I'm gonna say okay, yeah, when the switch is closed, like I said here, when this switch goes closed like this, now the supply VB is applied to the loop, and now current will start going. Okay, so when the switch is closed, the source VB is applied to the loop, okay, producing a current, an electric current, to pass through. So now you have current moving from the source into your loop. Okay, guys? And what will this causing here? Now you have a coil inside a magnetic field coming from the north and south pole like this. Now you have a magnetic field B going from the north to the south, and you have a coil which now having a current moving through this coil. Okay, like this. That's current moving through this coil or this loop. And that's now a typical case for a motor. Yeah? So the current, so let me say it. So now we have a current moving through a coil or a loop while cutting an external magnetic field. Okay, it's coming from the poles, the north and south poles. Okay, so a torque will be induced. Now you have a mechanical torque produced in this. Okay, and you can actually calculate this torque. If you remember this torque from the last lecture, it was equaling the constant K multiplied by phi multiplying by the current I. And this K, remember, equals ZP over 2 pi phi I. Okay, while Z is the number of conductors, P the number of poles, and phi the flux, and I the current. That is the very last thing we've been discussing in the last lecture. Keep that in mind. Okay, so now you have a torque. Okay, this torque causes the rotor to start rotating with angular speed omega m. Now the machine starts rotating. Okay, and that's it. Now you have a motor. Yeah, but the other thing we didn't talk about last time, and that's important to have in mind, keep just investigating what's happening. You know what will happen now. You have a motor that starts rotating. Okay, this means we have a coil rotating inside magnetic field. Remember this case? It's now the Faraday's law for generation. Now you have a coil moving inside a magnetic field and cutting it. Now an induced voltage will be just developed or induced in the coil. Okay, so a certain amount of voltage will be induced on this coil, E coil. Okay, and you can be calculating this to equal, so this torque coil and this E coil. The big idea, Z, or yeah, it is again the constant K phi times omega m. Now it's generation. So this equals ZP over 2 pi times phi times omega m. But wait a minute. It is now a motor or a generator, because you know now we have a torque and having an induced voltage, and we had to just understand this. Either the machine is a motor producing a torque, or it is a generator producing an induced voltage. But now we have both of them, and that's what's happening in a realistic machine, guys. It's a machine like this. You have a source like this applied, and now you have current moving through the coil. So you have a coil with a current moving through it while cutting the magnetic field coming from the poles. So now you have all the conditions to have a motor. So the machine is a motor and it starts rotating. So you now have electric voltage or electric energy converted to mechanical energy, and the motor starts rotating. Yeah, but while the motor rotates, now you have all the conditions for a generator also applied. You have a coil rotating inside a magnetic field, so induced voltage will be created on this coil. So you have this in your mind. In each motor you have inside the machine a small generator, another generator inside the machine itself. But now the more the machine will work as a motor or as a generator. Okay, it just happens by which one of them is higher. So this induced voltage E is less than the applied voltage. VB. And that's the whole point. This induced voltage that's being induced inside the coil will be less than the other one that's coming from outside, from this source. And that's why the machine is still a motor. You know what I mean? So that's a motor, but there is some induced voltage inside it, okay? And it opposes this applied voltage. So the induced voltage is less than the applied one and also opposes it. That's coming from Lenz's law. If you remember Lenz's law, so Lenz's law says that any induced effect will have an action that opposes the source of it. Okay, guys? And that is the very last thing we just entered the last lecture with. To have an equivalent circuit representing this, that will be R, and here is the external applied voltage, VB, and now there is the brushes and the induced voltage inside. This is E coil. You know the polarity for this applied voltage because that's applied voltage, yes? And you know now this induced voltage that will be just formed inside the coil because it's just moving now and cutting the magnetic field, will also have polarities plus negative like this because it has two opposites. So this voltage source will force current going inside like this, and this voltage will have these polarity because it's also trying to push current in the opposite way, because it's trying to opposite, to be opposing the effect of the external source. Okay, guys? That's Lenz's law. Yeah? But actually, VB is higher than E coil for a motor mode. Okay? If it doesn't like this, if E coil is higher than VB, that's now we're talking about a generator, not a motor. Okay? But it is a motor, the external voltage will be higher than the internal voltage and the current will go inside the machine, not outside of it. Okay, guys? So if you want to calculate this I now, the current will be basically VB minus E coil divided by R. The external voltage minus the internal voltage over R, or the induced voltage inside. Okay, guys? So that's what's happening here when you just switch on the switch, when you close the switch. Okay, guys? Now let me just elaborate more here. Okay? What will happen at the starting instance is just when you just closing the switch. Okay? At the very start, you have no speed because you're just now pressing the switch, and now the current is just starting to go inside the coil, and once the current go inside the coil will start rotating. But at the pressing instance, when you're just pressing the switch, the machine was not rotating yet. So this speed equals 0. And if you go back to the induced voltage law here, E coil equals some stuff multiplied by the speed, omega m. So if you don't have a speed at the very starting instance, you don't have any induced voltage at the starting. And that's what we said. This induced voltage comes after the machine starts rotating like this. Okay, guys? So before the machine starts rotating, at the starting instance, the induced voltage equals 0, and that means the current just equals VB over R from this equation. So this E coil will equal 0 at the starting instance. Okay? And that's the height. So this is normally very high value compared to running condition. Why? Because while the machine starts running, after the starting instance, the machine starts running, starts rotating, okay? Now you have a value for omega m. The speed starts going up, and that means the induced voltage over the coil starts going up, okay? And if you see this E coil in the equation here starts going up, that means I will start going down. So that means this starts going down. So that's a hint, a very important hint about any kind of machines, or most kind of machines you'll be dealing with, is when the machine's starting, when you hit the start button, the machine draws a very high current. We call it the starting current or the inrush current. Okay? And just after the machine starts rotating, this current starts going down gradually until it just goes to its regular running condition current. Okay, guys? That's a very important thing. You'll see it by your eyes in the lab, and you try checking this, and you'll see it in all the standard industrial facilities you've been just dealing with. That's all the time we try to deal with this very high amount of current the motor draws at the starting. Okay? Even it bothers the power system guys when trying to have planning of the protection device of the power system and all that stuff. If they have a big, huge motor on an industrial facility and this motor is trying to start, it may cause some disturbance in the system if this problem is not mitigated. Okay, so that's very important thing to have in mind, guys. A starting current of the motor is basically very high compared to the running current because of this. Because at the starting instance, the speed is 0 and the induced voltage inside the machine is 0. And this induced voltage is the voltage opposing the applied external voltage. And that is the thing that's control it, that's reducing the effect of it. Okay, so at the starting there is no induced voltage inside the machine because the speed is still 0, and that means the current will be very high because it will just equals the external voltage VB divided by the resistance, and the resistance is very low. Like we said, this resistance value is basically very low, and that means this current will be very high. Okay, but while the machine starts rotating, now you have a speed and you have induced voltage in the coil. Now this induced voltage starts going up, and that means the current will start going down. Okay, guys? So that, he was asking us what will happen when you switch on. He just asking you to discuss the just starting operation of the machine. What will happen when you just try to push the button and let the machine starting. Okay, guys? I hope you understand this. Okay, that was number A. Number B, what is the machine's maximum starting current? What is its steady state angular velocity at no load? He's asking you to calculate him the starting current. Make sure you're talking about starting current, the thing we just discussed here. And what is steady state angular velocity at no load? Okay, now we don't have load, or just let's find out what is the current first. So he's asking you, number B, about I starting. So like just we discussed here, I starting equal VB divided by R. Okay, guys? Because the induced voltage E equals 0 at the starting, like just we discussed here. So I'm gonna have this substituted. So VB equals 120 divided by R 0.3. That gives you 400 amps. That is relatively very high, and we see now when you just go forward. Okay, so that's the first thing. The other thing is asking you to find him omega m, okay, at no load. Okay, so we are talking now about a motor. So the load on the motor, the load on a motor is mechanical load. Obviously, you're talking about a motor, so the motor will just have a load which is mechanical attached to its shaft. While we're talking about a generator, its load will be an electrical load, a resistance, inductance, whatever it is. Okay, guys? So, if we are talking about a motor here, what's mean by this motor doesn't have any load? Because he wants the speed at no load. That means we're just letting the motor rotate while not attaching anything to it, while not attaching any load to it. Okay, that's not the typical case of anything, because we don't just grab a motor to let it run freely without driving anything. We will be attaching the load we want to the motor, whatever it is, a fan, a pump, a production line, some sort of a machine to just draw it, an elevator, a car, whatever it is. But now he's just asking you what will happen if you just press the button and let the motor to run freely without being attaching to any other kind of a load to drive it. Okay, so To understand what this means and the mechanical load and all that stuff, I'll have you now with the very famous mechanical equation of any motor. Okay, guys? Equal torque of the motor will equal the load torque plus B multiplied by omega m plus J multiplied by d omega m by dt. What, all of those? This, the motor developed torque. Okay, well, let me say it, rotor shaft torque. Okay, that is the torque produced by your motor. That is the value we've been just calculating all the time here, this value, T coil. But now we're talking about the whole motor. So it is a motor which have the multiple coils. That will be this value calculated, okay? So the torque that's coming out of your motor has to equal three parts. Number one is the load torque, and that's obvious, okay? I want your motor to derive some sort of a load, and this load has a torque for any value. So the load torque, the motor torque, has to be at least equal to this load torque. Otherwise, it will not be able to drive it. Okay? But what about those two terms, other terms? The other thing here, what we call a friction torque. This B here is the friction constant. It's not the flux density, guys. They just have the same name. So both of them are B, but this B is not the flux density, it's the friction constant, just a constant. Okay? That means you have also to overcome some friction happening, because, you know, guys, it's mechanical systems connected together. The motor is connected and the shaft of the motor connected to other mechanical system, and they are connected together. You have mechanical friction happening here, and you have to overcome this. Okay? It's not ideal. You're not just letting the motor being in the air like this. Okay? You have some friction and you have to overcome it. You have to produce an extra torque from the motor to overcome this friction, not just to be as much as the load torque. Okay? And what about this? That we call it the inertia torque. You know the inertia. The inertia is basically that means that any body with a mass, like the rotor or attached torque, whatever it is, will try to hold you back if you're trying to change its state from being just fixed, stationary, to be moving. Okay? It is just Newton's law. It's just saying that any body will just try to maintain its own state if it is stationary or moving. So if there is a stationary body and you try to move it, it will have some force trying to reply to you. Okay? And that's what we call the inertia. Okay? That's the idea. So if you're trying to move anything from its fixed position, and again this J is the inertia constant. Okay, so your torque produced by the motor has to be equal to the load torque plus extra torque to overcome the friction from the mechanical parts, and another extra torque to overcome the inertia if you are trying to move or to change the speed of this load. If it is fixed and you're trying to change its speed or just moving it, it will have some inertia applying to you. Okay? But the idea, it is just now depends on the time derivative of the speed, d omega by dt. That means that's just an inertia. So sorry, that is just a transient term. Okay, that is the transient term. Okay, that means this value, the inertia torque, disappears at steady state, and it's obvious. We're saying this inertia torque just appears when you're trying to change the state, to change the speed of the load. Okay, so if the speed is not changing, now you had just reached the steady state and the speed is constant. Now you don't have this term at all. But at the starting point, you have this term because the load was just at zero speed and you're now trying to make it rotate. So you're changing its speed. So you will have a value for d omega by dt. So this mechanical equation, guys, you'll find for any kind of a motor. It's not just for DC motors, but you'll find for any kind of a motor. It's just you have now, if this is the shaft of the motor, Okay, if the motor torque is just going this way, you will have other torques going the other way: the load torque, the friction torque, which is B omega m, and the inertia torque, which is J d omega m by dt. Okay, so your torque will be going one way, those three torques will try to go the other way. That means it's some sort of a brake on it. It's trying to oppose it, okay? So they're going to another direction, and your torque of the motor has to overcome their all, okay? That is the whole point here, yeah? So what is mean is just he wants you to find him the no load speed, the speed while there is no load here. That means no load means the load torque equals 0. He's saying it's no load, so there is no load torque, okay? What about the B omega m and the J d omega by dt, the friction and the inertia torque? If he's not talking about them, that means he's basically assuming they're 0. So if he give you a value for these, you take it toward you. If it's not, that means assuming they're 0, okay? And they should be very small values compared to the load torque, okay, guys? So yeah, it's realistic sometimes to just assume they are 0, okay, as long as you're just considering the load to be 0, okay? So if it is given a value for this friction and inertia torque, you just account for them. Otherwise, you just assume they're 0. So here, he didn't talk about them. That means he assumed they're 0. Okay? So the load torque is 0, B omega m is 0, and J d omega by dt is 0. And that means from this mechanical equation, the motor torque equals 0. Okay? At no load. Okay, guys? So now you have an equation, because this motor torque equals Zp over 2 pi times phi times I. Okay, guys? And from here, this constant will not be 0 anyway, and the flux will not be 0 because it's coming from the pools, and the pools is just given flux anyways. So what will make the torque equals 0? It is just the current equals 0. Okay? So for no load, there will be no current moving inside the machine. Okay? So yeah, it's not realistic again, guys, because even if there's no load attached to the motor, there'll still be some friction and inertia, but we just assume they're 0. They are not exactly 0, but they're very, very small, so we're just ignoring them. But in realistic application, they are not 0. They have a value, but it's very small. Okay, guys? So being this, if there's no load, the current will be 0. It's some sort of an ideal case. It's not a realistic case, but the current will be very, very small, so it is just can be ignored. Okay, guys? If the current is 0, and you know this current equals Vb minus E induced coil over R. This is the current value, and this equals 0. Okay, guys? That is the whole point now. Yeah? So, from this equation, Vb or E coil will equal Vb, because just Vb minus E coil over R equals 0. So E coil from here will equal Vb, and Vb equals 120. Yeah? And E coil equals Zp over 2 pi phi omega m. This equal 120. This equation for E coil. Z, guys, is the number of conductors. Number of conductors. How many conductors we have here? Just 2. We have just one loop, and this loop has 2 conductors, like we said before multiple times. And P is the number of poles. How many poles we have here? We have 2, just a north pole and a south pole. They are just 2 poles. Okay, it's just here in your drawing. So we just have a north pole and a south pole. We have 2 poles, and we have just 2 conductors. That is a conductor, and that is a conductor. It's just one loop, so it has 2 conductors. Okay, guys? Okay. Sounds good. So this is 2, the Z equal 2, and the number of poles is equal 2 also. Okay? And what about the phi? How to calculate it? Because all the time we just need omega m. That is the requirement for this question. He wants the omega m, the speed at no load. Yeah? So the all unknown here is the phi. And phi, the flux, equals B times A, the flux density times the cross-sectional area. So it's equal B, the A, the cross-sectional area, remember the last lecture, it's 2 pi RL over the number of poles. Yeah? We have anything here. You have R, which is the radius of the rotor, L, the length of the machine, P, the number of poles, which is equal to. Okay? So all of those are known for you. So you just substitute in this equation. So Z equals 2 minus, just multiply by 2, number of poles, so it's 4 divided by 2 pi. The phi equals B multiplied by 2 pi RL over P times omega m equals 120. You have everything here. The flux density B. You have the values over there. I'll just grab them for you. So the B equals 0.25. This R value will equal 0.5. And the L, the length of the machine, equals 1 meter. The P, number of poles, again equals 2. So you have everything in hand. You can calculate omega m at no load, which is just asked here, to be equals 480 radian per seconds. Okay, guys? So again, that's quantification of everything. Now I'm giving you an exact motor with exact dimensions and everything. I'm asking you if you just apply this amount of voltage to the motor and let it run freely without having any load, what will be the speed of it? You can do this in a lab, grab the actual motor and just apply the voltage to it and measure the speed. But again, we don't play with this. We want some sort of a modeling, mathematical modeling, to predict the machine performance. And here is the machine performance, and we are able to predict it just by modeling it, by using equations and an equivalent circuit like this. That is equivalent electric circuit like this. Okay, guys? And that's what I mean by modeling. Now we are able to predict the performance of the machine without sacrificing the machine itself. Okay, guys? Okay. So number B. Number C is saying that suppose a load is attached to the loop. Now we have a mechanical load attached to the loop. And the resulting load torque is 10 Newton meters. Now you have a load torque. It's not no load anymore. You have a load, 10 Newton meters. What will the new steady state speed will be? And that's a good idea. Because if you're applying a mechanical load to it, it will act like some sort of a brake. You are braking the motor some way. So if the motor is working at no load, that means it will be working at a high speed. But if you apply a load to it, it will brake it a little bit. So you're expecting the speed to go down. Again, talk to yourself like this. Adding a load to the shaft will act like a brake, so the motor will start to decelerate a bit. So you are expecting the new speed to be less than the no load speed. If it is not, that means you're doing something wrong. Keep that in mind. What would the new steady state speed be? How much power is supplied to the shaft of the machine? How much power goes to the shaft? That the mechanical power goes out. We'll be calculating this. How much power is being supplied by the battery? How much power, electric power, getting from the battery? Is the machine now a motor or a generator? And that's a good question. Okay, so we'll be just solving this one by one. So now we are on part C. He's simply saying that we have now a load with a torque 10 Newton meters. Okay, he's asking you to find him omega m, the new speed. And also he's asking you to find him the mechanical power going to the shaft. And he's asking you to calculate the power coming from the battery, which is electric power. Okay, guys? So the same exact procedure be talking about. Okay? So again, we know that the motor torque will equal the load torque plus B omega m plus J d omega m by dt. And he didn't talk about B or J, so we'll just assume they are 0. So the motor torque equals the load torque, and that's equals 10. Okay, guys? The same idea. What is the motor torque can be calculated like? It is Zp over 2 pi phi I. This is equal 10. Z equal 2 and P equal 2. Those are 4. So 4 over 2 pi times phi I equals 10. Again, 4 by 2 pi. The phi is again the B multiplied by A, which is 2 pi RL over the number of poles P. The same like before. Multiplied by I equals 10. Everything is known here. The B, the R, the L, the P, everything is known. You can just calculate I very easily from this equation. It will be 40 amps. Staying here, guys, very, very important. When you have some load attached to the motor and it's a steady state, see the current, it's 40 amps. That's the running condition current. Go back to your calculation before to find the starting current. Remember its value? 400 amps. And that's what I'm saying. The starting current is very high compared to the running current. And it has to be like this. So you are expecting this starting value to be very high and the running value to go much lower, like we just explained before. And that's again what I'm saying all the time. Look at the numbers you're having. It has to be realistic. Okay, guys? So that is the amount of current. Yeah? But we want to find the speed. Yeah? How to find the speed? Easily from the induced voltage equation. But rather you have a current here. You know this current equals VB minus E coil, the induced voltage, over R. Yeah? And this equals the current value, 40 amps we just found. And you know VB equals 120, R equals 0.3. So you can calculate E from here easily. E coil will equal 108 volts. Yeah? He was asking you if this a machine is a generator or a motor. You should be around this, but it's now obvious. As I said to you, for a generator, this E coil has to be less than VB. VB equals 120 and E coil 108. If it is less than this, that means it is a motor. Of the induced internal voltage is higher than the terminal voltage, that means the current will go from inside the machine to outside, and that means that's a generator because it's just giving you an electric current, not taking an electric current. Okay, so that's an answer to the question if this is a motor or a generator. You just calculated E, and it's now turned out this E is less than the applied voltage, so that's a confirmation that we are talking about a motor, not a generator. Okay, guys? And this value of E will equal Zp over 2 pi phi omega m. Again, you know how to calculate everything of this. It is Zp over 2 pi B multiplied by 2 pi RL over P, which is flux, so everything is just repeated here, times omega m. Everything is known in all these, okay? And you know E coil 180 like we calculated before, so the only unknown here is the omega, so we can find the speed omega 432 radian per second. Again, guys, see the value we got, 432. Remember the no load speed. What was the no load speed? 480. Like we said, adding a load means you have a brake applied to the motor. So you have this in mind all the time. If the load torque goes up, the speed will go down. So if I find you calculating this, and this speed turns out to be higher than the no load speed, you are making something wrong. And you have not to leave it like this. That means you're doing a mistake. Go back and find this mistake. It's very important. Okay, guys? Yeah. So that's the speed. Now we need to find the mechanical power. It's very easy. The mechanical power will equal the torque times the angular speed. That's equation to memorize. Have it in your mind. That's very important. The mechanical power equals the mechanical torque of the motor multiplied by the angular speed. The torque of the motor equals 10. The speed 432. So this power equals 4,320 watts. That's the mechanical power getting out of the motor. and he wants you to find him the electric power. Easy peasy. You're talking about a source and a current coming out of this source going to the motor. So it's like any circuit course we had before. It's the source voltage multiplied by the current coming from it. It's still a battery with a current coming out of it. So it's just you multiply the voltage by the current and you have the power. So it's 120 times the current, which is 40 in this case. So this is 4,800 watts. Seeing that? And it's another confirmation. The electric power is higher than the mechanical power because that is a motor. That is the way of the energy conversion. The electric power is converted into mechanical power, and it has the electric power to be higher than this because not all the power will be converted because you have some losses inside the machine. It's not an ideal system. We'll be talking about this much more in detail in the next lectures. Okay, but that's another confirmation. Now you have an electric power higher than the mechanical power. That means the input is an electric power and you lost some of it as losses and the rest is converted to mechanical power. So that means the direction of the power conversion or the energy conversion is electric power input is converted to a mechanical power, and now you have a motor. Okay guys, good. So that was number C. I'm gonna go back here to find number D. Suppose the machine is again unloaded. Now you take out the load and a torque of 7.5 Newton meter is applied to the shaft in the direction of rotation. What is the new steady state speed at this machine now, a motor or a generator? Saying this, that's very important. It's just saying suppose we took out the load and we applied an external mechanical torque, but now it is in the direction of rotation. Remember this, what will be the new steady state speed? Remember this here when I talked about the mechanical equation? This is the direction of the mechanical torque of the motor, okay? And that is the load torque. It's an opposite direction, acts like a brake because that's a motor. But what will happen if this mechanical torque, the load torque, is in the direction of rotation? So that is your shaft, and that direction of the motor torque. If it is the direction of the motor torque, that means there is the direction of rotation also. Omega m goes in this way. What will happen if you apply a torque, a load torque from other side in the direction of rotation? It will be now in the same direction. Okay guys, now we wanna find this. So the same idea again. We'll be using again the same mechanical equation. That should be D, I think. Yeah. Okay. Now the load torque equals 7.5 Newton meters, but I will be adding a negative sign. Why? Because it's an opposite direction to the ordinary way of the load torque. Now it's not an ordinary mechanical load because it's going in the direction of rotation. That means it's not a load, guys. It's an external force rotating the shaft. It's not like a load sitting there waiting to be rotated. No, it's a mechanical force. Something is trying to rotate your motor shaft. Okay, that's why I'm giving it a negative sign, because it's in the opposite direction of the regular load torque. Okay, it's negative because it is in direction of rotation. Okay, so again the same idea. The mechanical torque, the motor torque, sorry, will equal the load torque, which equals minus 7.5, and this equals again Zp over 2 pi phi I. You know how to calculate everything here, like just before. You can find the current will equal minus 30 amps. What I mean by minus 30, if you go back to our circuit, it was like this. That is VB, and that is E coil, and that was the resistance, and that was the direction of the current if you are talking about a motor, like we said before, because VB is higher than E coil for a motor. Okay, but what they mean, just the current now had a negative sign, that means the current is going outside like this, not inside. Okay, and what does it mean? We will just find out. Again, the I equals VB minus E coil over R, and it equals now minus 30. Okay, the VB still equals 120, R 0.3, so you can find E coil from here, and you will find it equal 129 volts. That is higher than VB, which equals 120. That means the machine now is generator, not a motor. And that makes sense. What I mean by a torque in the direction of rotation, that means you have an external mechanical power rotating the motor in its direction. That means you have an input mechanical power to the shaft. It's not just a passive load sitting out there waiting for your motor to drive it. No, it's a mechanical source giving more speed to the machine. Okay, guys? It's not a typical condition that you'll have the machine, you have just a mechanical source from outside and also applying an electric source from outside. If it is a generator, it's just a mechanical source from outside, and you have a magnetic field source, and that's it. You have a generator and you have electric power out. If it is a motor, you're applying external electric source like VB here, and just waiting the machine to rotate and rotate on another load. But it's just some sort of theoretical case to test your understanding of what this happens. If it is still a motor and rotates and everything, and you applied another source of mechanical power to rotate the shaft even more in its direction, you will now turning this machine from being a motor to be a generator, just like we noticed here. Okay, because you applied another mechanical torque in the direction of rotation, the speed went up higher. Okay, how you know this? Just will be going, because he wants you to find him the speed. E coil equals ZP over 2 pi phi omega m, and now it equals 129. You know how to calculate phi from previous thing, so you can find omega m easily from this to be 516 radian per second. Remember this value? The no-load speed of the motor was 480. So this value of speed is higher than even the no-load of speed. The no-load speed is the higher value the motor can reach. Okay, guys? We know this. We said that before. The motor, if it has no load, the speed will be the maximum. And then while you get more and more load, it breaks the motor, so the speed went down. Okay, guys? What does it mean now if the speed is higher than the no-load speed of the motor? That means you have an external mechanical source is pushing the machine more and more speed. This high speed will make the induced voltage E coil higher than VB. And now the machine is just turned out to be a generator, not a motor. That's the basic idea. We know this before. A generator needs speed. You rotate the machine with a speed inside a magnetic field and you have induced voltage. That is the idea. This machine was a motor and just rotating in a certain way, in a certain direction. You applied external mechanical force to add even more rotation, more speed to the motor in its same direction. It just kept doing this until the induced voltage inside the machine went higher than the external source, and now the machine has just turned out from being a generator, from being a motor, to be a generator. Okay, guys, just a reminder here. If you're talking about a motor and this is your shaft, okay, the mechanical torque, the motor torque will be like this, and the load torque will be in an opposite direction. Are we talking about a generator? And that is your shaft. If this is the direction of the machine's torque, or the motor torque, the mechanical torque will be in its same direction. And that's why we are just headed with a negative sign like this. Okay, guys? And you see this. Now your speed is very high. It's higher than the omega m no load of the motor case. and that's why it now turned to be a generator rather than it would be a motor. Okay, guys? Good. Fine. Yeah, that's very good. We still have one given thing at the end. It's just he's changing the value of the flux density and asking you what to do. It's easy, we're just using the same equation to do it. I will just upload you the answer for this one. It's very easy to have, it's just straightforward substitution in the equations and you will get the answer. Okay, so I hope that was informative, and I think you have a lot of information to have here, so please have some time to review and study this once and once more. Thanks so much for joining me today, and I hope to see you next time.